Okay, great. So this is our second speaker for today, Rémy Dubertrand from Northumbria University, and he will talk about ergodic and non-ergodic many-body dynamics in strongly nonlinear lattices. So, Rémy, you can.
Thank you, Thibaut, and thank you for my colleagues. I wanted to thank you for sending me away from my other colleagues and visit Cambridge, but I guess that for today we will do with a virtual event. I wanted to speak today about some recent results I have obtained, and I hope you will allow me to follow a slightly different format, in a sense that I think I've come up with a model which can be tackled especially well with techniques coming from nonlinear PDs, and I would try to convince you that there are some interesting questions relating to that, and also maybe ask you some question how to address such problems. So this is a work which I did in collaboration with my former colleagues in Regensburg and Mr. Sandy, who is in Princeton. So I will start maybe with a motivation, and just to settle the language, to settle the common ground, let's start with maybe some basic things. So I will deal exclusively with a Hamiltonian system, so classical system, which is defined in a 2D dimensional phase space, and the Hamiltonian defines a classical flow, which can be also written as the Hamilton equations, which I repeated here. And the main idea is to ask whether the flow or this time evolution is ergodic. And for that, I need a definition of an observable, which is for me just a smooth function of the phase space coordinate f of xp. And then the Hamiltonian flow or this time evolution is ergodic if for almost all initial conditions and for any observable f, one has that the time average on the left in the long time limit coincide with the phase space average on the right, where mu is some invariant measure under the flow. And when we are dealing with ergodicity, I think there are at least two very different directions. One is to go into small dimensional phase space, and one very standard types of problem is the billiard problem. So for example, inside a plane, so here the dimension of the phase space would be 4, dimension of the position space would be 2. And in that problem, the trajectories are given by geodesics, which means a straight line, and specular reflection at the boundary of the domain. So take, for example, an ellipse. You start with some initial condition, with some initial position and some initial velocity, and then it will hit the boundary. Whenever it hits the boundary, you have the optical law of reflection, meaning that the angle of reflection is equal to the angle of incidence. And these types of models, seen as dynamical systems, have been very intensively studied also in the mathematical communities. And just to give you a small summary, so you have on the one hand the integrable shape, so the ellipse, rectangle, and a few triangles. And then on the other end of the hierarchy, you have ergodic or even hyperbolic billiards. So this is sometimes called the Bunimovich stadium. And these things with a circular obstacle is called the sinh billiards. And what is important also is that in the middle, you can have a whole type of intermediate situations. So for example, rational and irrational polygons and other types of domain with scatterers. So the way to achieve ergodicity in small dimensions is usually, one efficient way to achieve ergodicity is to start with an integrable Hamiltonian and perturbing it. So start with H0, which is an integrable Hamiltonian, and then you add a small perturbation. Epsilon is a small parameter. And then you have altogether a non-integrable system. And well, the main result, which is especially powerful in this small dimension, in the low dimensional phase space, is that for small enough epsilon, most of the invariant tori coming from the integrable structure of H0 will survive. And this is this very, very fundamental result known as the KAM theorem. And if you want to have some more physical perspective, you could have a look, for example, at this book. So the idea of today is to go instead and visit the large dimension of the phase space. And already there, for example, my understanding, with my limited knowledge, is that this is still an active research area in KAM theory. So there are, of course, all this family of integrable PDEs, which correspond exactly to the, let's say, being infinite. But whether they can be a classification, at least for me, it's still unclear. So, and I'm happy to learn some references or some suggestion if you have. The interest of having a phase space with very large dimension is clear in physics to define statistical mechanics. So basically, if you want to describe small volume of gas like the air in the room, you are immediately dealing with an absolutely huge number of particles. And in order to take a statistical description, you have to assume what is sometimes called the ergodic principle, meaning that the typical trajectory of a physical system is ergodic for large enough dimension. And I think that this ergodic principle is actually much more difficult to state in a more rigorous term. So associated to this idea of ergodicity is the more physical idea, more intuitive idea of thermalization, which has to do with understanding the long time behavior of a many-body system. And to understand it, there have been several approaches. For example, in physics, there has been the kinetic theory using the H theorem, and then a hydrodynamical approach. And we are probably going to listen more about this, especially for integrable system later today. And on the mathematical side, having a rigorous result to state and prove the ergodic principle, at least to my knowledge, only works for the Lorentz gas, where we can map the problem into an effective one-body problem. Oops, sorry. So thermalization can be defined or would require quite a long definition. So for me, and for today, it will be enough to assume that thermalization coincides with ergodicity of the trajectories. And another motivation, which unfortunately I will not be able to touch today, is that thermalization in quantum system has had a renewed interest recently due to quite impressive experimental progress, for example, when dealing with gas of cold atom. And in particular, from numerical experiments or from cold atom experiments, one can see that there are two main roads to have a failure of thermalization, which is first integrability, and this would require a generalized notion of thermalization, or disorder. Sometimes this is, I mean, especially with all the current activity of many-body localization. So the question of today, the plan of today is to consider a classical nonlinear chain with capital N sides. And the first question is, does it thermalize? And if it does, how does thermalization occur in the limit of large N? An alternative question is, what can lead to failure of thermalization in such a system? So before I go further, if I talk to you about classical nonlinear chain, you will immediately probably think about the Fermi pasta Ulam Tsingou problem, when this was considered a long time ago. So basically, the idea was to consider a linear chain perturbed by a non-linear interaction term. And so this is exactly as I said before, this is the integrable part. And then you add a small non-linear term. Alpha is the perturbation parameter. And the idea of the numerical simulation, which was quite remarkable at that time, was to say if one excites, if one put all the initial energy in one mode of the integrable Hamiltonian, due to the nonlinear interaction, the other modes could play the role of a thermal bath, and the whole chain would finally equilibrate in the sense that all the modes will have the same amount of energy after long enough time. And this would be valid for even very small alpha. And instead, what they saw is here. So here you have the plot of the energy of the linear modes as a function of time. So only the mode, what they call mode 1, is excited. And after a relatively short time, all the energy comes back to the same mode, and all the other modes are losing energies. And so this is called recurrences. And they were very surprised at that time to see their recurrences instead of equipartition. And in particular, these recurrences can be seen as a sort of ergodicity breaking. So this actually led to this breakthrough by Kruskal, Zabrowski, and others to map this problem to the integrable Cordovec-de Vries equation for large n, which could actually explain this sort of recurrence phenomenon. There has been alternatively also other criteria to set a threshold over which the chaotic dynamics will finally occur, and this is the resonance overlap criterion by Chirikov and collaborators. So after all this motivation, I would like to come more precisely to the model I want to present you today. So this model consists of n non-harmonic oscillator which interact quadratically with each other. So the Hamiltonian looks very simple. So you have kinetic energy and interaction. And the position at each site is given by a small n dimensional vector. But the twist here is to put a billiard boundary condition on the amplitude, on the value of x. So the vector x can be seen as the coordinate of a point, and this point has to sit inside a domain. So the dimension, for example, of my phase space is the dimension of the vector at each site times the number of sites. And what I claim is that having this free Hamiltonian supplemented with this billiard-like boundary condition is enough to create ergodicity and I think very rich collection of new phenomena. So maybe another way to illustrate my Hamiltonian, I rewrite it here, is that you have a sequence of billiards, and each particle inside a billiard is related by its neighboring, it's related to its neighbors via quadratic interaction. So this is the case when I have only a scalar quantity at each site. But of course, one could imagine something more sophisticated when we have a two-dimensional vector at each site, which is whose amplitude has to obey the constraints of a chaotic stadium. In order to make the problem well defined, I need to have a boundary condition for the dynamics on the chain. I don't think they would be relevant for large n, but in our work, we decided to take periodic boundary condition. So if I go a bit more precisely to give you the dynamical equations, again, they look very simple. So you have the Hamilton equations or the time evolution equations, which are simply the equations of a free evolution, but they are supplemented by this constraint of having each position vector, the position vector at each side being constrained to be inside a domain. And this letter constraint makes the model not a perturbation of a linear model. The Hamiltonian is also not analytic nor smooth. And also conversely to the Fermi pasta Ulam and Tsingou situation, there is no translation symmetry here. Of course, it is still an Hamiltonian system with a time-independent Hamiltonian, so the total energy is conserved. And if I look at the energy per site, small h, there are clearly two limiting cases. One is when this small h is much larger than 1, then the problem looks like non-interacting particles. So the interaction becomes less relevant, and we have almost independent particle trapped inside a potential well at each site. On the contrary, when we have the small h being much smaller than 1, we will have a free linear chain which will have seldom contacts with the wall. So again, as I try to do it in the motivation, maybe I will try to distinguish between low dimensional phase space and large dimensional phase space. So for low dimensional phase space, I rewrite the Hamiltonian for the lowest non-trivial, simplest non-trivial situation when I have interacting with each other. And for example, at each well, the position has to be between 0 and 1. And for such a low dimensional phase space, a very powerful to analyze the dynamics is to use what is called the Poincaré surface of section, which is a way to have a stroboscopic view on the I was here, I guess.
Yeah.
Can you hear me now?
Yeah, we can hear you.
Okay, sorry about that.
No problem.
So I was saying that for the case of two particles, the phase space is 4-dimensional, and for that we can use the idea of the Poincaré surface of section to visualize the trajectory. And in particular, this is very powerful to distinguish between two types of trajectories. So on the one hand, you will have situation when the trajectory will cross the section having a set of intersection points which is dense and seems with structureless, and this is the case for ergodic trajectories. On the other hand, here or there, you will have a set of intersection points which will lie along the smooth curves, and this is the non-ergodic or integrable-like behavior. So what you can see is that changing the small h, which was the energy per site, you can see that you evolve from a mostly chaotic phase space to here, this situation which can be seen as actually a weak perturbation of indeed independent particle trapped inside a wall. For that case, the Poincaré surface of section will be trivially horizontal line, and here you can see that the small interaction or the large small h, if you want, leads to small perturbation of this situation. So that was the idea to understand the structure of the low dimensional phase space. If we go to large dimensional phase space, I'm not aware of any tool to have such precise description of the phase space. So what we decided to do numerically was to evaluate the stability exponent, which becomes the Lyapunov spectrum in the long time limit, as a measure of chaos. So we are dealing with a Hamiltonian system, which means that each of these Lyapunov exponents can be sorted in pairs of positive and its opposite value. So I'm only showing here the positive part of the Lyapunov spectrum. And the different colors stand for different size of the chain, if you want. And what you can see is that, first of all, A, B, and C correspond to different value of the parameter H, the energy per site. So what you can see is that when the size of the chain increases, you have a convergence towards a smooth curve, if you look at the red dots. And unfortunately, our numerics are not, I mean, it's difficult to draw a definite conclusion about our numerics, but it seems that all but one Lyapunov exponent would remain positive in a large, at least in a large N regime we could investigate. So this would also motivate the idea that our system is not only ergodic, but even hyperbolic for large N. And I'm coming here to a slide which I think is very important, hopefully for you. This is where I can make the connection with nonlinear PDE. So in order to investigate more precisely the continuum limit, I don't know how to do it. I don't know how to implement this billiard. Well, it's not completely clear, I should say. I have an intuition, but I have not a definite idea how to define this billiard boundary condition in the continuum case for a field. So one road to take to achieve that would be to first smooth the trapping potential at each side by a smooth function like here. And then we are left with some well-defined analytic Hamiltonian. So this is what I do here. Instead of the billiard boundary condition, I put this potential in the limit with the parameter alpha. When alpha goes to infinity, this potential forces the position to be between 0 and 1. And the rest of the Hamiltonian is just the same. So you have kinetic and interaction terms. And then if you have such a smooth Hamiltonian, you can take the continuous limit replacing, okay, there are several steps, but I guess you are all familiar with them. So if you take a chain with a fixed length and you assume periodic boundary condition, you can replace the variable at each discrete site by a field of a continuous space variable. And in particular, you can come up with a field theory defined by the following Lagrangian. And from this Lagrangian, you can write the Euler-Lagrange equation or directly write down the PDE associated to this model, which take this form. So you can see you have something like the wave equation, and then you have exponential terms. And probably many of you in the audience will recognize this as being a sine-Gordon equation, which is known to be integrable. So my question for you would be how to analyze what happens when I take this equation and I send alpha to infinity. So basically our study, our result makes us believe that you will break integrability, one will break integrability. But for me, it would be, I think, very important to try to understand how this happens and to which extent. So in particular, it is important to see that it is not so obvious to have a small parameter to go from a smooth integrable situation to the actual billiard problem I'm interested in, but at least I wanted to share with you the road to go there with this. So just to repeat, one of the take-home message here is that when I take this PDE, which I know is integrable because this is just a deformation, I mean, via rescaling and change of variables, I can rewrite it as the sinh-Gordon equation. My question would be how the integrable structure of this PDE evolves when I send my parameter alpha to infinity. So in a way to assess thermalization from a physical point of view, we also consider the following observables. So I told you before that thermalization was about the time average being equal to the phase space average for certain observables, for all observables. So here we choose one common observable, which is a 2-point correlation function. And here the bracket stands for time average. And basically the results are shown here. So please forget about the red curve, which I can explain, but not of direct relevance for us. So what you can see is that if one zooms in, you will see that there are several curves, the green, yellow, and the blue, which are all time evolution of this quantity, time average of this quantity for a growing sequence of the size of the chain, capital N. And then hopefully you can see the black dashed curve here is the phase space average. So when growing N, the time average seems to, at least at the numerical level, it seems to converge to the phase space average. And so in that sense, we can say that we see ergodicity for this system. I guess time is running a bit out, so I'm not sure. How long do I have, Thibault?
You still have 3 minutes because we started a little bit later.
Okay, so then I will just say a few words, not to burden you too much. So the idea is that once we see that for generic trajectories, the time average is equal to the canonical phase space average, we wanted to see where there could not be some regular sub-manifold in the phase space when there would be more regular behavior. And actually, we identified a few of this region, and I'm not sure I can go into the details of them, but basically we wanted to see, we wanted to address the 3 following questions. So for which value of the total energy we can have a regular subregion in the phase space? Can we estimate the volume of this subregion and how this volume scale with the size of the chain or the dimension of the phase space going to infinity? So the first fact is actually very easy. The first question is very easy to answer because as we have a billiard boundary condition, if we have a solution of the free problem which does not touch the boundary, then it is also a valid solution for our billiard problem. So any free evolution will, which doesn't touch the wall, will be a solution of our problem. And actually, it is very easy to convince yourself that you can find such a solution for arbitrary large value of the energy. So I'm afraid that as time is running out, I will not cover the more precise set of initial conditions that we found, which leads to non-ergodic behavior. Just to mention that also, I think I stopped the full screen mode. So the when we do the thermodynamics analysis, we perform the thermodynamic analysis for this model as well. So in the simplest case of scale available at each site, and the central quantity to be computed is the partition function, the canonical partition function. So actually, we use a transfer operator technique to recover the 2 limiting regime of the mean energy per site. And in particular, one could explain the energy equipartition in those 2 limits. We can go even a bit further by using a more refined approximation and evaluate the critical exponent for the 2-point correlation I was showing to you before. So this -1 here can be more technically proved. And this brings me to the final discussion and conclusion. So as I promised, I would like to share with you the following question about the model. The first is, can you suggest, what could you suggest as other ways to quantify ergodicity and chaos, and especially efficient in a limit of large n? And this could be alternatively formulated as how to assess integrability for large chain, and how to assess the lack of integrability in this regime. Another question which could be very important, for example, if you want to quantize the model, is to understand how to estimate the region of stability of a periodic orbit. And the things that I wanted to mention really is how to describe the change of space when the parameter alpha, which is smoothing the wall, is sent to infinity. So that brings me to my conclusion. So I tried to describe to you a new model for the dynamics of a nonlinear chain. It has linear dynamical equation, but still it is not a perturbation of an integrable model. So KAM theory is not directly applicable, at least to my understanding. It shows on a numerical level signatures of ergodicity, but I think there are several perspectives, in particular changing the shape of the billiards when you have vector fields at each side, and analyzing the effect of the symmetries, and distinguishing between slow and fast thermalization, and also discussing common points, differences with the Fermi pasta Ulam and Tsingou problem, and a quantum version of this problem is also on the agenda. Thank you very much.
Thank you, Rémy. Thank you. Very nice talk. So we have time for questions or comments or answers. So Alex Torvis wrote in the chat that I guess it will be singularly perturbed Sine-Gordon equation. So answering your question concerning. I don't know if you want to elaborate on that, Alex, or.
Hi. Yes, I think when in the limit, when alpha goes to infinity, right? So that means that your differential part, right, of this equation, it's the same as put small parameter in front of second derivatives, right? And then will bring us to semi-classical or singularly perturbed or semi-classical sinh-Gordon. And I don't know about sinh-Gordon, but for Sine-Gordon, Peter Miller and his colleagues have developed theory of that. And so there might be some with many interesting phenomena happening there. So it might be relevant if written in for sinh-Gordon.
Thank you very much. That's very helpful. Thank you.
You're welcome.
Thank you, Alex. We have a question by Vincent Caudrelier. So not sure if this is a relevant question at all, but has the regular subregion you mentioned got anything to do with scars in billiards? If so, would quantizing your system lead to some understanding of quantum scars?
So regular region would be, yes. So I think the regular region would correspond to initial condition, which would lead to locally integrable dynamics. And as it is, I mean, if I understand the question correctly, I expect that yes, in the quantized version of the model, this regular subregion would lead to quantum scars, quantum anybody scars here. I hope I answered the question. Please let me know if not.
Okay, yeah, Vincent, thank you. And then we have a comment from Benjamin Doyon on the thermalization. There is a mathematically rigorous notion of the Hilbert space of extensive conserved quantity. It is finite dimensional in usual chains, infinite dimensional in integrable chains, and they are involved in ergodicity-related processes.
Okay, thank you. Yeah, thank you about